We're starting Unit 5, which is from the data at hand to the world at large. This looks at inference, which is using statistics to make decisions and determine if something should or should not happen. We're going to start with Chapter 18, which is Sampling Distribution Models. This chapter contains quite a bit of information, and it's pretty important. We will break it down as we keep going throughout the year and keep kind of coming back to some of this stuff. But without this chapter, we really couldn't do anything else for the rest of the year. So it's pretty important. We're going to start by talking about sampling distribution models. A sampling distribution model shows the behavior of the sample statistic, either a mean or a proportion, over all the possible samples for the same sample size n. What that means, let's take a coin for example. If you were to flip a coin 100 times, and you were to calculate the proportion of times it landed heads, whether you got 48% or 49% or 50 or 51%, doesn't matter. If you were to bring that in and we were to plot that, that would show us the distribution of how many heads we would expect to get if we were to flip a coin 100 times. So a histogram of all the possible samples is modeled with the normal model to get insight to how much the sample proportion or the sample mean will vary from sample to sample. This informs us about the amount of variation we should expect when we take samples. So for example, flipping a coin or rolling dice. So again, back to the coin, if we were to actually do that, and I were to have all of you flip the coin 100 times, and you came in and you plotted it, we would end up with a roughly unimodal and symmetric distribution, where it's going to be centered right around 50% because that's what we would expect to get. But it won't all work out. Some of us will get over, some of us would get less, but we would be able to see the amount of variation that we would expect. So we could tell that, okay, getting 52% heads is not that big of a deal. But if somebody came in saying they got 70%, that probably would be. So sampling distributions allow us to see how much variation we expect. You could do the same thing with rolling dice and averaging them together. If you roll multiple dice together and you average what they came up with, you're going to get really close to the center. If we were to all do it and do multiple samples and then plot it. Sampling distributions will follow the normal model. It's only going to be an approximation, but the greater the sample size, the more accurate and appropriate the normal model gets. So if we were to flip a coin 10 times versus 100 times, when we flip the coin 100 times, it's going to be more accurate. If we were to increase that to 500 times, it will get even more accurate. So the larger the sample size, the more appropriate the normal model ends up becoming. But because we get to use the normal model, we can use the 68, 95, 99.7 rule or the table or our calculator to be able to calculate those probabilities, which is really actually kind of nice. Because sampling distributions look at the amount of variation, we're going to talk about sampling error. Sampling error is the fact that the proportion or the sum varied from group to group is called sampling error. By the way, this should say or, not of. We expect there to be some variation. I don't expect, if you were to flip a coin 100 times, all of us to come in saying that we got exactly 50%. No, there's going to be some variation. That is to be expected. That is what is called sampling error. It isn't actually error. It's not actually a mistake. It's just the variability you expect to see from one sample to another. The better term is sampling variability, but we call it sampling error. I want to go through the notation that we will use with sampling distribution models, because this will be the same notation that we end up using throughout the rest of the year. So a lowercase p is the true proportion. This is the actual proportion of the data. It's never going to change. In flipping a coin, it would be 0.5, 50%. P hat, P with the little hat on it, is the proportion we get from a sample. So if you were to flip that coin 100 times and it landed 48 times on heads, then you would have 0.48 as your P hat. This is the proportion you see from the sample, and it will change from sample to sample. We expect that. For a mean, Y bar is the sample mean, and mu is the population mean. We'll use sigma to represent standard deviation for both the proportions as well as means. So if we're using a modeling distribution for proportions, we need parameters. So our parameters for any normal model are the mean and standard deviation. So the center of the histogram is at P. It's a true proportion. So the mean mu is equal to P. And the standard deviation for proportions would then be the square root of PQ over N. So this gives us a normal model of P, comma, square root of PQ over N, where we have our mean and our standard deviation. There are assumptions and conditions for us to be able to use a sampling distribution model for proportions. The first one is the random condition, which states that the sample needs to be taken randomly. Then there's the 10% condition, which should look familiar. It states that the sample size n must be no larger than 10% of the population. And then there's the success-fail condition, which should also look familiar, which states that the sample size has to be big enough, so both NP and NQ have to be at least 10. So we need to expect at least 10 successes and 10 failures. And again, in order to use a sampling distribution model for proportion, you must check these conditions. So let's move on from proportions to means. So the means is the average of one die. If you average one die, it's just going to be what it is. So if we start with a simulation of 10,000 tosses of a die, a histogram of the results is shown. It is uniform. We expect that. If you roll a die once, 10,000 times, you would expect that each number would occur roughly the same amount of times. But as we increase the number of dice to calculate that average, that mean value, we're going to get closer and closer to the actual population mean. I have two examples here. The first one, we're looking at the average of 2 dice after a simulation of 10,000 tosses. We are pretty much perfectly unimodal and symmetric, where our center is in between 3.5 and 4, and we go from 1 to 6, which makes sense. If we increase to 3 dice, we get this. This is still roughly unimodal and symmetric, but if you notice as we increased it, our chances of getting the small values decreased, and we get closer and closer to that center value. If we look at increasing the dice to 5 dice and rolling 5 die at once, averaging the results and plotting it and doing that 10,000 times, we get a histogram that looks like this, where again the center is now much closer to 3.5, which is what the real center should be. And if you notice, our outside values are kind of disappearing. They're becoming less and less likely, and we're getting closer and closer to that actual center. If you were to increase the dice to 20, you're increasing your sample size now. After a simulation of 10,000 tosses, it ends up looking like this, where the center is clearly at 3.5, and those extreme values have just shifted in towards the center of the histogram because they become less likely. So as you increase your sample size, you're going to have less variability, and you're going to become closer and closer to your actual center. This would work too for proportions, but I'm just demonstrating it here with means. So for a mean, the mean and standard deviation, the mean would be y bar, and the standard deviation of y bar is sigma over the square root of n, where this sigma is the standard deviation of the population. So like the actual standard deviation, and it'll always be given to you. There are assumptions and conditions for using a modeling distribution for sample means. The first two are the same, the random condition and the 10% condition, but the last one is a little bit different. So for proportions, we check the success fail, but for means, we check what is called the large enough condition. This condition is a little bit in the gray area because it doesn't specify how big the sample size actually needs to be. But if we have a population distribution that is roughly unimodal and symmetric, then it doesn't need to be too big. But if the population distribution is bimodal, skewed, or something else, then it's going to need to be a larger sample size. The fundamental theorem of statistics. Okay, so this is it. This is the important piece here. This is why we get to do everything else that we're going to do. The sampling distribution of any mean or proportion becomes more nearly normal as the sample size grows. These observations need to be independent and random. What this means is that the larger the sample size, the more nearly normal it's going to be. So increasing the dice from 2 to 3 to 5 to 20, it became more and more normal. Same thing would happen if you were to increase the number of times you're flipping the coins, whether it's 10 or 100 or 500 or 1,000, you're going to get closer and closer to the center. This is what the central limit theorem states, which, by the way, is abbreviated CLT. The mean of a random sample has a sampling distribution whose shape can be approximated by a normal model. This is pretty much what I've been saying. As you plot multiple means or multiple proportions of repeated samples, it's going to follow the normal model. The larger the sample, the better your approximation will be. For the record, central means fundamental. It does not refer to the center. The cool thing about this is that it works even if the population distribution is bimodal, skewed, or anything else. For example, if you were to look at the heights of 7th graders, it might be skewed because some kids are hitting a growth spurt and some kids have not yet. So you kind of vary a little bit, so maybe the distribution is skewed. I don't know, I'm just going to pretend. So if the distribution of their height is skewed, it doesn't matter because of the central limit theorem. As long as we are looking at repeated samples and not just one sample, we'll end up being able to use the normal model. The central limit theorem does not say, though, that the data are normally distributed as long as the sample size is large enough. For example, if we were to take a sample of 50 7th graders and plot their heights, and it ends up being skewed, if we were to increase our sample size and go to 100 7th graders, we would probably still be skewed. In fact, we would probably expect it to be even more skewed, because we actually expect that if the population data is skewed, then as the sample gets larger, then the skewedness will become more defined. What the central limit theorem is talking about is the means or proportions of repeated samples. So if we were to take multiple samples of 50 7th graders, average their heights together, and plot their average height, then we're going to be unimodal and symmetric. Same thing works for proportions. So you have to be careful when you're talking about the central limit theorem because we have two different distributions. We have the real world distribution of the sample, which is just one sample, just looking at the data of one sample. That is going to have the distribution that it's supposed to, whether it happens to be unimodal and symmetric, or it's bimodal, or it's skewed, doesn't really matter. Because when we look at the math world, the sampling distribution of the statistic, that is what's modeled by the normal model. So the real world distribution of the sample, that's modeled by the histogram, or a bar graph, or a table. But the math world, that is repeated samples, multiple samples, not just one, but multiple. And then all of those proportions or all of those means plotted on one plot. That's then what can be used with the normal model. But which normal? We have two. We have proportions and we have means. For proportions, the mean is the sampling distribution is centered at the population proportion, which is P, where the standard deviation is sigma equals the square root of PQ over N. For a mean, the sampling distribution is centered at the population mean, and then the standard deviation is sigma over the square root of N. These did not stay where they were supposed to be. This y bar should be right here, and this y bar should be right here. So it should say standard deviation of the sample mean is sigma over the square root of N. And again, sigma is the standard deviation from the population. Okay, great, but when should we use proportions and when should we use means? When we have categorical data, we calculate a sample proportion, p hat. When we have quantitative data, we calculate the sample mean, y bar. So it depends on the data. If it's categorical, we use a proportion. If it's quantitative, which means we have units on our data, then we use a mean. But this is it, and I hope you guys have a good night. I'll see you tomorrow.